Hello again, everyone. This video is going to go over the solutions to the second free response practice test for AP Physics C Mechanics. So let's go ahead and dive right in. Okay, so first of all, I've got written up here the point allotments for each of the 5 parts of question number 1. So this problem actually has a little bit of everything here. There's conservation of energy, conservation of momentum, and some stuff about circular motion and kinematics as well. So part A asks for the speed of the person just before collision with the object. So we have a person sitting at point A, holding this rope of length L. They swing down here through the circular arc, and at point B, they collide with a second object with mass m2, hold on to it, and then let go of the rope, and they travel through the air to part D. So for part A, we just want to know how fast is the person going when they reach part B, but before they collide with the object. So for this problem, we want to use conservation of energy. The person is losing gravitational potential energy as they swing from point A to point B, and that is being converted into kinetic energy. So we can say that the change in potential energy plus the change in kinetic energy must be 0. The change in potential energy will be negative, so I'll just move that to the other side of the equation. So the magnitude of the change in potential energy will be the mass of the person, m1, times g, times the vertical distance they travel through, which is L. That's going to be equal to their kinetic energy, which is 1/2, times their mass, times velocity squared. And I'll call this v1 because there will be another velocity that we calculate later. So we just have to rearrange this. Notice the m1 cancels on both sides, so we'll get 2gl equals v1 squared, or v1 equals the square root of 2gl. All right, so moving on to part B, we want to know what is the tension in the rope just before the collision. So we have the velocity of the person at point B, so how does that relate to the tension in the rope? Well, if you imagine the forces that are acting on the person when they're at point B, there's going to be a gravitational force pulling them down, and there's going to be tension in the rope pulling them up. Now, these forces will not be equal because this person is in the process of swinging through a circular arc, so there is going to be a net upward force, which must be equal to m times v squared divided by the radius. And let's call this m1. All right, so from Newton's second law, the net force in the upward direction is going to be T minus m1g, and that has to equal the centripetal force m1 times v1 squared over r. R is the radius of the path, which is also just L, and v1 squared from part A is equal to 2gl. So we end up with T minus m1g equals 2m1g, or the tension equals 3 times m1g. All right, so the tension is equal to 3 times the person's weight when they reach point B. All right, so now in part C, we want to know the speed just after the collision. So this person grabs onto the object with mass m2, so this is going to be a totally inelastic collision. We can say the momentum before the collision is equal to the momentum after the collision. Before the collision, the momentum is m1 times v1, the same answer that we had to part A. After the collision, we're going to have 2 objects in motion, so the mass is m1 plus m2, and then let's call v2 the velocity that we're actually solving for. So this v2 then is just going to be m1 v1 divided by m1 plus m2. And then we sub in our answer from part A, so we get m1 over m1 plus m2 times square root of 2gl. All right, so that's 3 parts down. Part D requires a little bit of calculation. It wants to know the ratio of the kinetic energies before and after the collision. So we have all of the pieces that we need for this part now. We just have to sort of plug everything in. So the initial kinetic energy before the collision, we just have the person with mass m1 in motion. So the kinetic energy will be 1/2 m1 v1 squared. And again, if we plug in our answer from part A, v1 squared is 2gl. So our kinetic energy is just going to be m1 times gl. Okay, after, we have the person plus the other object. Kinetic energy is going to be m1 plus m2 as the mass, and then our velocity is going to be v2 squared. So we have to plug in our answer from part C. So this is going to be m1 squared over m1 plus m2 squared times 2gl. So a couple of things will cancel here. The 1/2 and the 2 will cancel. m1 plus m2 will cancel with one of the factors down here. So we end up with m1 squared gl over m1 plus m2. Okay, so we want the ratio of the kinetic energies, so we just have to take this and divide it by this. So I'll have to go to the next page to do this. All right, so we had m1 gl, and then dividing by the final kinetic energy, I'll just flip this fraction over, and then we're going to have gl down here. So m1 gl will cancel and leave just m1 down here. So we end up with just m1 plus m2 divided by m1. So after all that, we end up getting this nice, fairly simple expression for the answer to part D. All right, so finally, part E asks for the total horizontal displacement of the person from position A until they land in the water. So if we go back to our original diagram here, this x is what we are trying to find. Okay, so we know the velocity with which this person leaves point B to soar through the air and fall to point D. So what we need to do here is find the time that it takes them to fall a distance L, and then multiply that by their horizontal velocity. And that is going to give us the distance from the edge of the cliff to point D. All right, so let's call that distance x1 here. So that is going to be our velocity at point 2 multiplied by time. So what is the time? Well, the time that it's going to take the person to fall a distance L, since I start with 0 velocity in the vertical direction, we can say that L is equal to 1/2 g times t squared. So t is going to be 2L divided by g square rooted. All right, and then V2 is our answer to part C. That was m1 over m1 plus m2 times root 2gl. And then the time is root 2L over g. All right, so when we multiply these two square roots, the g's will cancel. So we have root 2L times root 2L, so the square root just goes away. We get m1 times 2L divided by m1 plus m2. Now, fortunately, if you got to this point here, this is worth, I think, 3 of the 4 points for part E, but it is not the final answer. We have to remember to add the horizontal distance between point A and point B, which is L. So our answer is going to be this thing that we just calculated plus L, and we can write this with the same denominator as the first part. It's just multiplying it by 1, so we can combine these fractions. So we're going to end up with a common denominator m1 plus m2, and then on top we're going to have 2m1l plus m1l, so it'll be 3m1l plus m2l. So that is our answer to part E. All right, moving on to question 2. This one is more of a experimental analysis question. So we have this setup here with a block hanging from a pulley, and you're given a table of data as well and asked to make some interpretations from that data. So first, however, part A, we just want to calculate the linear acceleration of the falling block in terms of the given quantities. So the given quantities are the 3 that are marked in this diagram, and then we also know the time t, that's the time for the block to fall. All right, so this block falls from rest, so we can use a kinematic equation to say that the distance that it falls, d, is equal to 1/2 times its acceleration times t squared. Remember, this is not g times t squared because it will not be accelerating downward at a rate g. The tension in the rope will slow it down somewhat. But this equation will still be valid, so we can just rearrange this and say the acceleration is 2d divided by t squared, and that's it for part A. This one, by the way, is worth 2 points. So if you want to know the point breakdown for this question, A is 2 points, B has 3 separate parts to it. Those are worth 2, 3, and 2. C is worth 4 points, and then D is worth 2 points. Okay, excuse me. Okay, so for part B, we want to know what quantities should be graphed in order to determine the acceleration of the block. So you're given a table of values for the distance that the block has moved for different values of time. So if you look at this equation that we just gave for part A, we could rearrange this and say that d is equal to, well, we could just go back to the first equation here. D is equal to 1/2 at squared. So this looks like we want to plot d versus t squared. And then it should give you a reasoning that the slope then will be equal to 1/2 of the acceleration. Now, believe it or not, this is actually one of many possible answers to part 1 of question B. And you could also say that you would plot v versus t. You would have to do a little bit of work to figure out the velocity values that you would calculate, or even a versus t. This one maybe even seems a little bit circular, but if you calculate an acceleration value at each moment of time, you should get a roughly horizontal graph. So the best fit line will have an intercept, and you can take that intercept as the experimental value of A. Or you can even say that you're going to plot d versus t, but in your justification, you would have to say that this graph would be a parabola and that the second derivative would equal the acceleration. So they'll accept any of these. For this one, by the way, it would be the slope that equals the acceleration. So of all of these choices, the one I would go with is probably this one. This is the most direct and the easiest one to do with the data that you have. All right, so in part 2, they want you to actually graph this. So they give you a little chunk of graph paper here. So you need to make sure that you label your axes here. So we're going to plot d versus t squared. Looks like this scale here would probably be the best. So distance ranges from 0 to 2. T squared will be in the range of 0 to 2 as well. And if we do this, we should get a series of points that are all pretty close to a straight line right down the middle of this graph. So if you do this, you would actually have a ruler for your test. So you sort of eyeball the slope here, and remember the slope of this graph is not the acceleration; it is half of the acceleration. So you should get an acceleration of roughly 2 meters per second squared. All right, moving on to part C. C asks you to calculate the rotational inertia of the pulley in terms of M, R, A, and some fundamental constants. This one is maybe the trickiest part of this problem. So let me show this picture here again. So we can write equations that govern the motion of the block and the pulley. For the pulley, we have the net torque equals I times alpha. This is Newton's second law for rotating objects. The torque is coming from the tension in this rope. Right? So this rope is going to pull down on the pulley and up on the box. So the torque is going to be the tension times the lever arm distance, which is the radius of the pulley. That's going to equal I, which is what we're trying to solve, times alpha. And there is a relationship between the angular acceleration of this pulley and the linear acceleration of the block, which is alpha equals A divided by the radius of the pulley. All right, so we can say that I is equal to T times R squared divided by A. All right, so what is T? Well, if we look at the forces on the block, we have mg pulling it down, tension pulling it up. So our Newton's second law equation for the block, mg minus t equals m times the acceleration. I'm defining the acceleration of the block to be down to be consistent with the acceleration of the pulley. So this tells me that t is equal to m times g minus a. So that needs to be plugged in up here. So the moment of inertia is going to be r squared divided by a times m times g minus a. All right, so that is our expression here. Or if you prefer to rearrange it, you could also write it like this. Keep in mind, this m is not the mass of the pulley, believe it or not. It is actually the mass of the block. So it might look a little strange to express the moment of inertia this way, but this is really all we have to work with. Okay, so part D, this is more of an analysis type question. You have to really think about this one. So it tells you that, say you measure these quantities and you figure out the rotational inertia of the pulley, and then, or you calculate it rather, and then you find some other way to experimentally determine the rotational inertia, and you find that it's actually greater than what you determined from your experiment, and they want you to give one explanation. So in other words, this pulley has some true value of its rotational inertia, but when you do this experiment to try to calculate the value, you come up with a number that is smaller. So one thing that might immediately jump to mind is saying that friction is the explanation here. But if you think about it, friction would cause the pulley to rotate more slowly than it should otherwise. So that would cause the block to descend more slowly, and that would make the pulley to appear to have more inertia than it actually does. Right, so that actually will not work here. There's a few things that you could use for explanations. One is you could say that maybe the string was wrapped around the pulley too much so that the effective radius was actually larger. So if the string was, further out here, pulling on the pulley, that would result in more torque, which would make the pulley rotate faster. So if the pulley rotated faster, then you would interpret that as having a lower moment of inertia than it otherwise would have. So that's one possible explanation. There are some others, but I just want to make sure you come up with some explanation that results in the pulley, appearing to have less inertia than it actually does have. All right. Okay, so let me move on to number 3. This one deals with a rotating hinged object. So this is some material from the rotation unit. So we have a bar with mass m and length L, and there's a pivot attached 1/3 of the way from one end of the pivot. And the first question is just to find the rotational inertia. So we have two formulas for the rotational inertia of a rod, but neither of them works for the pivot that is somewhere off center like this. So we know if the axis is through the center of mass of the rod, then the moment of inertia is 1/12 ml squared. If the axis is through the end, then it's 1/3 ml squared. So the center of mass one is actually the one that's useful here because we have this thing called the parallel axis theorem. So in case you don't remember, the parallel axis theorem says that if you have an object with a pivot at some arbitrary location, then the moment of inertia for the object rotating around that point is always equal to the center of mass moment of inertia plus some extra term. And that extra term is just the mass of the object times d squared, where d is the distance from the center of mass to the pivot. So in this case, d would appear to be 1/6 the length of the rod. So that means our moment of inertia is going to be 1/12 ml squared plus m times 1/6 L squared. So this is 1/12 ml squared plus 1/36 ml squared, which is 4/36, which is 1/9 ml squared. All right, so that's our answer to part A. This is 4 points, by the way. So this one, most of the value of this question comes in part B. So part B says that, okay, we release this thing and let it swing downwards, and we want to know how fast is the tip of this bar moving when it swings through the vertical position. So this is a conservation of energy problem. We have gravitational potential energy being converted into kinetic energy. So what we have to realize here is that for a rotating object, the change in its potential energy can just be determined by looking at what happens to its center of mass. So when this thing is hanging vertically, let's see, do I have the vertical picture here? Yes. The center of mass of this object, which is right here, has moved down some distance. It used to be horizontally in line with the pivot, and now it is moved down by this distance, which is 1/6 L. So the change in potential energy is minus mg times 1/6 L. And that is going to be equal to, actually let's do this. Negative the change in potential energy will be equal to the increase in kinetic energy. So the kinetic energy of this thing we can treat purely as the rotational kinetic energy using the moment of inertia that we calculated in part A. So it's equal to 1/2 times the moment of inertia times omega squared. So if we put these two things together, we have 1/6 mgl equals 1/2 times our moment of inertia, which is 1/9 ml squared times omega squared. So m and l will cancel. We'll have 1/6 g equals 1/18 L omega squared. If we clean this up a little bit, we'll get 3g over L equals omega squared, or omega equals root 3g over L. All right, so we are almost there. What we actually want is the linear velocity of the bottom end of the rod. So this thing is moving in a circular path. The velocity here is going to be related to the angular velocity. So the velocity of the end of the bar is going to be omega times r, which is the radius of the path that it is tracing. So the radius is going to be the distance from the pivot to the end of the bar, which is 2/3 the length of the rod. All right, so we just need to take omega, multiply it by 2/3 L. So that'll be 2/3 L times root 3g over L. And we can simplify that a little bit if we want. We can move the 3 inside the square root. We can move the L inside the square root as well. That should give us 2 times root GL over 3. So they would probably take the previous expression here as well. I don't know if you have to have it fully simplified, but this should be our answer to part B. All right, so this very last part deals with oscillations, which is now no longer part of the AP test according to College Board, but I will go ahead and go over that solution just for completeness. So let me put the picture of the vertical bar back up. So now the question is, if we just pull this thing a little bit to the side and let it swing like a pendulum, what would the period of its oscillation be? We went over the differential equation that you would use to find the oscillation period of a simple pendulum in class. So let me show you how that would be modified for something like this. So let's imagine what happens when we have this thing pulled to the side by some distance. So the center of the mass is over here, this point marked X. Gravity is going to pull down on this with some force mg, and that's going to create a restoring torque. So let's say theta is the angle by which this has been displaced. The torque here is going to be the force mg times this lever arm distance, which is still 1/6 L, times the sine theta. And it's negative because this is a restoring torque, just like the force from a spring is negative. All right, so Newton's second law says that torque is equal to I times alpha. So the torque is minus mgl over 6 times sine theta. That is equal to I, our moment of inertia from part A, times alpha. And remember, alpha in terms of calculus is the second derivative of theta. If you're not familiar with this notation, it is the second derivative of theta with respect to time. That's what the theta with 2 dots on top of it means. So I'll just use that shorthand notation here. So if we rearrange this a little bit, 1/9 ml squared times second derivative of theta plus 1/6 mgl sine theta equals 0. I'll cancel m and l, and let's move everything so that I have just theta doubled out by itself over here. So this is going to be 3/2, 9/6 times g over L times sine theta equals 0. And then if this is a small angle, the small angle approximation says that sine theta is roughly just theta. So we have an equation that looks like x double dot plus some constant times x equals 0. That's what we saw when we studied simple pendulums, and what we saw was that this constant here is equal to the frequency squared. So the same thing works here. The frequency of this pendulum squared is going to be 3/2 g over L. So omega is 3g over 2L square rooted. Okay, so it wants to know the period of oscillation. So omega is equal to 2 pi divided by the period. So if we rearrange that, t is equal to 2 pi times the square root of 2L over 3g. And like I said, this particular material will almost certainly not be on the AP exam, but it still is an interesting problem, so that's a solution if anybody was interested. All right, thank you so much for watching.